Now we want to look at the actual method for homogeneous of degree. So I have two examples. My first example is y dx equal to 2 times quantity x plus y dy. Now you can get it in the form y dx minus 2 x plus y dy equal to 0. That way you have it in this form of m dx plus n dy equal to 0. So you just need to make sure the m and the n are homogeneous of the same degree. Well, in this case, y is obviously homogeneous of degree 1, and I can put in a lambda and factor a lambda out, so n is also homogeneous of degree 1. Just to show you, m of lambda x, lambda y would be lambda y, which is lambda times m. And then n of lambda x, lambda y would be minus 2 times lambda x plus lambda y, which would be lambda times minus 2 times x plus y, which of course this is n. So they're both homogeneous of degree 1. So therefore, let's choose our substitution. Now, this is where I talked about in class about if m is quote unquote simpler or easier looking than n, then use x equal vy. Well, I've got y as opposed to negative 2 times x plus y. Well, obviously y is much easier or simpler looking. So therefore, I'm going to use the substitution x equal to vy. Now, I'll be honest with you, it wouldn't have been that much harder to use the other one, y equals vx, but let's go with what we said. It's simpler, so let's use x equal vy. So dx is equal to v dy plus y dv. Again, all I did was use the product rule. So now let's substitute these into my original differential equation. So this would be y times dx is v dy plus y dv minus 2 times x is vy plus y dy equal to 0. So now, once I have that, let's start putting items or terms together that are alike. So let's write this out a bit. So this would be yv dy plus y squared dv minus 2, and I'm going to factor out a y here, and this would be v plus 1 dy equal to 0. Now the reason I did that is because now I've got my v's, so it's a separable differential equation. I can take these v's and put them together. So let's take this term and put together with this term. So what do I have? First of all, I have the y squared dv. So I'm going to take a dy out, and what do I have? I have plus yv minus 2yv minus 2y. And of course I have equal to 0. Well, what do I notice now? I notice that I've got y squared dv plus, so I've got a yv minus a 2yv, so that's a negative yv, minus 2y dy equal to 0. So I can continue on. Y squared dv. What can I factor out? Well, I can factor out a minus y, and I end up with v plus 2 dy equal to 0. Now it's ready to separate the variables. So I come up here, and what do I have? I have a dv over v plus 2, and I have a minus dy over y. The y's cancel out, equal to 0. So I can integrate everything. What do I end up with? The natural log of v plus 2 minus the natural log of the absolute value of y. And if you don't mind, instead of writing plus c, I'm going to write natural log of c. Why do I do that? Because I've already got natural logs in here. So let's put them together. This would be natural log of v plus 2 over y equal to natural log of c. So this would be, using the properties of natural log, this would be v plus 2 over y equals c. But when you start off with x's and y's, you want to end up with x's and y's. So I'm going to replace. I go up here to where I did my substitution. X equals v times y. So v equals x over y plus 2 over y equals c. Now, what I can do, I can simplify this somewhat. So this is x over y plus 2 equals c times y. But then I can get a common denominator, cross multiply by the y. So all I'm doing is getting a common denominator. So this would be x plus 2y equals c times y squared. Now, that's simplification. You could have stopped here in my class without the simplification, but the book will oftentimes simplify. So that's why I went ahead and simplified for you. Let's take a look at this IVP. It has an initial value. So I have 2x squared dy dx equals 3xy plus y squared. Well, the first thing is I need to get it in the form of my homogeneous of degree. So m dx plus n dy equal to 0. So I'm going to cross multiply by the dx and then just bring this over here. So I have 2x squared dy, cross multiply by the dx and bring it over the other side. So minus 3xy plus y squared dy equal to 0. So this is my, this is a dx, sorry, so that's a dx. So this is my n, this is my m. Now why did I say this was n? Because n goes with the dy, m goes with the dx. So what I have here is that n of lambda x lambda y equals 2 lambda x quantity squared, which is lambda squared times 2x squared. So it's degree 2. It's homogeneous of degree 2. M of lambda x lambda y, what would that be? Plug in. Now there's a negative there, so don't forget about the negative. So this would be negative quantity 3 times lambda x times lambda y plus lambda y quantity squared. So what do you get there? So what do I notice I can factor out? Well, I've got a lambda times a lambda, which is a lambda squared there. I've got a lambda squared here, so I can factor out a lambda squared. What's left? Well, I've got a negative times quantity 3xy, okay, plus this y squared. Well, look at that. This inside here is m. So this implies degree 2. So it's homogeneous of degree, both of them are homogeneous of degree 2. So now I can choose which substitution I want to make. Well, I look at this, the m and the n. The n looks simpler, so let's use y equal to v times x. So therefore, dy equals, again, the product rule, v dx plus x dv. Okay? So let's substitute in. So I take this, and I'm going to get 2x squared times quantity v dx plus x dv. Over here, I'm going to get minus 3x times vx plus y. Again, y is vx, so that'd be vx quantity squared dx equal to 0. So let's write all this out. I like to write it all out to simplify it. 2x squared v dx plus 2x cubed dv minus 3, and I'm going to distribute that 3, x squared v dx minus v squared x squared dx, of course equaling 0. So now let's put apples with apples, oranges with oranges. So I'm going to put all the dx's together. So, and I notice that in each of the dx's, I have a v or a v squared, but I also have an x squared. So the x squared is common to everything. So let's factor out an x squared dx. And what am I left with? I'm left with a 2v right there. I'm left with a minus 3v right there. And I'm left with a minus v squared right there. What term does that leave me? That leaves me plus 2x cubed dv equal to 0. Now I've gone ahead and erased the second part of the board because I'm going to need it here in a second, but let's go back to our problem and let's go ahead and separate the variables. So what do I end up with? So I end up with, and I'm going to take the 2 over here, so this would be dx over 2x because it's x squared over x cubed is 1 over x. I'm going to bring the 2 with it, plus dv. Now let's do this. This is 2v minus 3v. 2v minus 3v is a negative v, so I'm going to have a minus v squared equal to 0. So let's rewrite this. So this would be, again, dx over 2x. Let's put the negative out front and let's break it up. So this would be dv over v times v plus 1 equal to 0. Now, if I were integrating all this, this first one's easy, but the second one, I have to go back to something I learned in Calculus 2, probably in Calculus 2 for most of you. I have to use partial fractions. So I'm going to set it up, 1 over v times v plus 1, and I'm going to write it, since these are both linear, I'm going to write it a over v plus v over v plus 1. They're both linear, so I put a single digit up on top. Now I cross multiply, in other words, I multiply everything times v plus 1. So on the left, on this side, I get a 1. On the v times v plus 1, the v's cancel, so I end up with a times v plus 1. On the next term, the v plus 1 and the v plus 1 cancel, so I end up with plus bv. So I end up with av plus a plus bv. Now, put like terms together, so this would be a plus b times v plus a. Now this is where I like to say set kumquats equal to kumquats, oranges equal to oranges, apples equal to apples, watermelons equal to watermelons. So the constants I have are 1 on that side and a on that side. So that one's easy. 1 equals a. How many v's do I have? Well, I don't have any v's over here, but I have a plus b here. Since a is 1, 1 plus b equals 0, that implies that b is negative 1. So now I take a look at this over here and I rewrite it with all this. So I have dx over 2x minus, now that minus is going to come through here. So this becomes a minus dv over v. And this negative, a minus a negative becomes a positive, plus dv over v plus 1 equal to 0. So now I can integrate, because I just separated. So I'm going to get 1/2 natural log of the absolute value of x minus the natural log of the absolute value of v plus the natural log of the absolute value of v plus 1. Here again, since everything is natural logs, instead of writing plus c, and the integral of 0 is c, why don't we make it natural log of c? And we'll make c a positive constant. So now, let's use property of natural logs on this side, and let's put them together. Let's multiply through by a 2 first, and then let's put them together. So I'm going to have the natural log of x times v plus 1 squared over v squared equal to the natural log of c. Now again, I multiplied everything by a 2, and then I used the properties of natural logs. ln of a minus ln of b is ln of a over b. ln of a plus ln of b is ln of a times b. So that's the properties I used. Then the fact that natural log is a 1-to-1 function. So ln of a equal to ln of x means a equals x. So in this case, x times v plus 1 squared over v squared equals to this positive arbitrary constant. Now I go back right here where I said y equals v times x. So that's the same thing as saying y over x equals v. Let's plug that in. So I have x times y over x plus 1 quantity squared over y over x quantity squared equal to c. Now again, I'm going to flip that denominator over, so this x squared right now is in the denominator of the denominator, but when I flip it, it comes up on top. So what do I end up with? Here's what I end up with. I end up with x times y over x plus 1 squared times x squared equal to c, but this side is all over y squared. When I take that x squared inside the square, here's what I end up with. So I end up with x, take this x inside, so it loses its square once it gets inside that square. So what do I end up with? Y plus x quantity squared equal to c over y squared. Now I come back to here to this initial condition, which I've already circled for you. So the initial condition, the y is the -2, the x is the 1. So let's plug in right here. Let's just plug in x equal to 1, y equal to -2. X equal to 1, y equal to -2. So let's just do that. -2 plus 1, of course, is -1, but it's squared. So I get a 1, and in the denominator, I get a 4. So therefore, c equals 1/4. So I can go right here, and I can now set that equal to 1/4. So I could, if I wanted to, I could cross multiply by the 4, cross multiply by the y squared, and so what do I get? I get, when I cross multiply by the 4 times x times y plus x quantity squared equals cross multiply by the y squared, and so I get 4 times x times y plus x quantity squared equals y squared. This is in simplest form, But once you plugged in this, you could have just left it right there, like that. Either way would have been fine. So this is homogeneous of degree. I either use y equal vx or I use x equal vy, substitute in, and I get a separation of variables problem. Don't forget, though, if I start with x's and y's, I must end with x's and y's. No v's, no w's. Always x's and y's if that's what I started with.